Hello viewers, and welcome to a new STM32 World tutorial video. In some previous videos we introduced FreeRTOS as an operating system for STM32. It was videos number 27 and 28. In the first video we introduced the general concepts of FreeRTOS and how to put that together, and in number 28 we added some statistics to be able to debug how this is actually running. Now, none of the stuff we did in these videos was particularly useful, except perhaps the statistics, but nevertheless, as a demonstration, it was okay. Today, we're going to try to actually use this for something constructive, something useful. So let's look at briefly the code. As usual, I've took the FreeRTOS 1 project where we did all this, and I have created a new project which I call FreeRTOS 2, which is essentially doing exactly what I said. We create the setup with the FreeRTOS. In FreeRTOS we create a couple of mutexes to give exclusive access to printing and to the LED. We create a semaphore which is used to synchronize the LED toggle task, and we create a queue where we can send messages to be printed out every second, and we created some tasks to handle all this. Running this as usual, let's try to run this. And I have the serial output down here, and you can see it runs and it prints a tick every second, and every 10 seconds it shows the task list there. And if we look at the device, you can see it blinks the LED. I have hooked up the oscilloscope to the DAC, the DAC outputs, and what I intend to do today is essentially replicate what we did in an earlier video. You can see it up here, the one I called DAC 1. In that we were creating a sine wave on one of the DACs and displayed that. Today we are going to be a little bit more ambitious, and we are going to create a sine wave on both the available DACs and show how that can be done with FreeRTOS. So without any further ado, let's dive into it. So up here, the first thing we need to do is to actually enable the DACs, and as I said, we will be using both of them. So I enable both of the DACs. There is no way we can do this in real time, so we also need to create a couple of DMA channels to be able to feed this. So we create one from DAC 1, and you can see it is a stream. We will make it circular, and it sends 16-bit values from the memory to the device. Let's create one more channel. So we add for DAC 2, which is stream 5 and stream 6 in the DAC, and that too needs to be a circular buffer, and we increment the address of the memory as we send it out. So that is the basic DAC. We also need a timer to run this, and I actually forgot the numbers how I did this, so let me cheat a little bit, but for once I'll show you the cheat, because I actually did it in this project, which I haven't talked about, but let's see how I actually configured the timer. I can't remember. It's easier to look at the old project. There we go. What timers do we have? We have timer 6 and we have timer 4. Oh, which one do I actually use? Hang on, let me check. I start both of them. Why do I do that? me look at the DAC, how we trigger. We use timer 6 in both cases, so it's timer 6 we want to be looking at. So timer 6, so 84 minus 1, that divides down to 1 megahertz, and then we divide further by 10, so 100 kilohertz sample frequency is what we will be looking at. So let's go into this one and create that timer. So here we create timer 6. Remember, the timers in the STM32F405 is being fed off of this bus, which is running at 84 megahertz, the APB1 timer clock. So it's running at 84 megahertz. So we go in here, we activate the timer 6, we divide this by 84, but these numbers have to be minus 1, so we divide this down to 1 megahertz, and then we divide it further by 10, so 10 minus 1, and we end up with 100 kilohertz sample frequency by doing it this way. So let's go back to the analog and the DAC, and we need to trigger this one from timer 6 trigger out event, and we need to trigger this one from the trigger 6 out event. So both of the DACs are triggered from the same, running with the same clock frequency. We look at the interrupts. We have not enabled the global interrupt. We don't need that, but we need the DMA stream to trigger the interrupt, because they are the one we're hooking at. Now let's look at the FreeRTOS setup for this. We need a little bit extra stuff in here. We need an extra task to do these calculations of the sine wave. So let's go in here and we create a sine task and start sine task will be the command to start it. And we should probably give it a bit extra memory. It's a bit stingy. So there we have a sine task. We also need a queue, because what will happen is, we know that from the previous video, is that the DMA transfer will trigger an interrupt, and we need somehow to tell FreeRTOS what it needs to do, the sine task, what it needs to do. So let's add a sine queue, and the queue size, that's more than enough, but we will do a pointer to something we'll send to this. So let's do a uint32t as our message between the task, and let's create that. So we now have a sine task and we have a sine queue defined. So without further, let's generate the code. Now I have cheated a little bit, of course, since I did this in a project I haven't talked about, and I have the source code of that project open, so I am probably going to steal a little bit here and there and do some copy paste. It will be faster and less boring. The first thing I want to do is to define a couple of type defs. We need a way to communicate between these the interrupt to the sine task, and I will create, and we need a way to keep the data between the sine wave. The sine wave, the way it works is that the DMA interrupt, we will do the entire buffer, so we need a place to store the floating, the angle and the angle change and the amplification between the changes. and we need a pointer to the buffer. So we create a type def to have that. We also need to create some defines, and we have them here. Basically, I want to set the DMA buffer size. We could set it to 64. We could also set it to 32. It doesn't matter really what that size is, as long as it doesn't get interrupted 100,000 times every second. So we set a sample frequency of 100,000, which we calculated. The clock frequency 84 megahertz divided by 84 and divided by 10. Now the DACs are 12-bit, so they can have values between 0 and 4096. So we set the midpoint. We have the midpoint of that will be 2048. So because it's a sine wave, we need negative values and positive values, so we need to run it around this value. Now we need to create a couple of variables to hold this. First of all, let's define our buffers. We do that down here with the private variables. We already have the timer tech, but let's create a couple of buffers. Now the buffer is a circular buffer. So we have a DMA buffer 1, DMA buffer 2. It's a circular buffer, so we put it at 2 times the buffer size. That is our actual. So there'll be 256 bytes each is being used for these buffers. Now let's create the temporary storage to store these waves data in between. So we create an array, array or two of DACs, and each of these DACs will have a pointer to the relevant DMA buffer. It will have a starting angle. It will have a frequency. We set this to 1000 Hertz. The frequency calculation is always a frequency 2 times pi divided by the sample frequency. That is the angle change per sample. And we set an amplitude. We could set this to 0.8 just to make it visible that these two are different. I don't want to repeat this calculation constantly, so I'm going to create a variable here which I'll make a const, which basically contains a value of 2 pi. The reason for that is the entire circle is 2 pi, and once the circle is complete, we basically subtract that value from, so that value will be used quite a lot. So we need a 2 pi. I do not understand why that is not defined in the C libraries, but it isn't. If we look at this app, oh yeah, okay, it doesn't know where to find that. Let me go up. I forgot something here. Up here we need to include math.h. I think I can probably find it now. Let's try to build the project. So far it doesn't fail. Before I forget it, no, I have that already, so it's okay. Now we should be able to look at mpi open declaration, and it finds it there. So it's got all these constants in the C headers, the standard C headers. It's got like pi, it's got half a pi, it's got a quarter of a pi, but for some bizarre reason it doesn't have 2 pi, which is the full circle. It is of course easily calculated, just multiply that by 2, but I don't like to do too many floating points calculations if that can be avoided. Next up is, let's create our, actually I want to, next up, let's fire up the timers and the DMA. I need to have that here, so that will be down in our normal main. Once we have started everything, we can fire up these timers. So we're starting the timer in interrupt mode. That's actually not necessary, but we might need to. I don't think it. I don't know. I don't know if it's actually necessary to use the interrupt there. It probably isn't. And then we start the DMA on the HDAC channel 1 with the DMA buffer 1, 2 times the DMA buffer size, and we do that for both of these DACs. We also need to look at the callbacks, because we know from the earlier video that whenever these DACs need more data, they will fire an interrupt, which will result in a callback. So let's add these callbacks up here. So basically we will have a DAC callback channel 1 when it's half used. Now, the reason why we double the buffer, and it's a circular buffer, is that we can't modify the data that we are working on. So basically there will be an interrupt when it starts. When it's half through, there will be an interrupt. That is a signal to us that we can now start to look at the first half of the buffer while it is processing the second half. Then, so you can see what we're doing here is, I don't want to do that. That was we'll enable that if we have problems. That was just a counter so I could see how many there was. So we can see we take that DACs and we set the buffer to our DMA buffer 0, which at that point will contain all zeros. We also take the we create a DAC address, which is a pointer to that, and we sent that on the queue. We sent the DAC address. Now, it is vitally important when you're using OS message queue put in a callback, which is an interrupt handler, that we don't set a delay for. If we look at the format of this, it is basically the handler to the queue, the pointer to the message that you want to transfer, a priority, and a timeout. We cannot have a timeout. So this will fail, and we could introduce a further error checking on the result of this OS post. But if the queue is full, it will fail, because it can't put any more on the queue. But as long as the queue is empty or near empty, we will be allowed to put this on the queue immediately. So this will run really quick. Just continuing that we have the callback when it's entirely done. When it is entirely done, we will set the half point in the DMA buffer, and we'll continue from there. We'll switch between handling the first half of the buffer and the second half of the buffer. Now we are doing exactly the same with the channel 2, which is here. It is I don't know why that is in a different library, but that's how ST wanted to do this. So now we actually only have one thing left, and that is deal with this in the Sine task that we created. Let me just find, I have it here. So it will be down towards the end. Start Sine task. Here, wait, no, down towards the end. Start Sine task. Here it was. So we basically have the start Sine task, which at the moment is doing very, very little, not to say nothing at all. Let me cheat a little bit and copy from the one I already made. So we go in here and we copy this, and let me go through what I'm actually doing here. First of all, I declare a couple of variables, one for the return code of the OS message queue get, and a pointer to the Sine pointer to that Sine struct. So this is what we met. We get a message, we wait for a message, we get the address of this in here, and in this case we wait forever for this kind of message. Then we will, again, I'm doing some calculations there, we will create this pointer for the Sine QT that points to the value we just got. And then I go through the array with the buffer size, one at a time, through this array that we will have inside this, and we will create the sine wave following exactly the same calculations as we did in the previous one. I think I missed another. Let me just look how this is done. I think I need to include that ARM math because I'm using ARM's math library. We might also need to enable that inside. Up here we need to include this one. Let's see if it will build, otherwise I'll have to go in. We don't have it, so we need to go into this, and we need to go into CMSys1, and we need to enable the DSP. We select that as a library. That is a DSP library. Okay, and generate the code. Let's try to build. It still didn't work. Did we must have forgotten something in here. CMC, oh, I didn't enable that. Okay. I just made it available for QMX, but I didn't actually enable it. So let's see if it works now. Project built. And there we go, no error. So we now, just to go through, we have the interrupts which are generated by the STM32 DAC, and we use that callback to trigger a message, and then we have a task inside FreeRTOS which is handling that buffer message and do the sine wave calculations. Well, without further ado, let's try to run it. And let's start by looking at the serial output. If anything is happening, I'll let it run. I can tell you there is a problem, but I don't know what it is yet. Let's see if we get the sine task gets no work done. So the message is not actually sent to the sine task. Did we enable the interrupts? That's always the first thing to check. NVIC, we have the DMA stream. What we did not do, DAC, we didn't enable this global interrupt. I didn't think that would be necessary. It could also be the timer, couldn't it? So let's look at the timer 6, which is the one we're using. Trigger. I didn't send the update event. That might actually be it. So let's do the generate code of that. See if that gets better. And try to run this. And I can tell you straight away that is better. So let's look at now. First I want to show the stats. And we can see that now the stats are actually operating. The sine task is actually operating 15% of the time. And the reason I could tell you very quickly that it works is if I look at the video of the device, you can see that we have a DAC 1. We have two steady. Now let me start by seeing what we should expect to see. and we have that defined up here. Where was it? Here. The first DAC will run at 1 kilohertz with basically almost 1 in the amplitude. The second one will run at a slightly lower frequency. That means they will be out of sync with each other, and a slightly lower amplitude. And if we look at the device, you can see that is exactly the case. The yellow one there is the 1 kilohertz, which is the one I'm triggering on the scope, and the other one is slightly lower amplitude and slightly out of sync. Now, just to show that we can experiment with this, of course we can switch this off, and we can change this to make it slightly even smaller, and we could set it at a lower frequency to make them out of sync. Can you say more out of sync? Yeah, you can actually, I guess. So let's see how that looks. Now I have a bigger difference between the two, so they are more out of sync. So that is essentially it. We can see FreeRTOS can easily handle interrupts that happen quite often. I mean, a buffer of, how often does this happen? A buffer of 64. So we are running at 100,000 hertz. So well, let's so we will have, let me find the calculator there. So we are running at 100,000 divided by 64. Must be it, right? Divided by there. So we are getting about 1,500 interrupts per second per channel. So about 3,000 times each second. This DMA buffer calculation will have to be calculated, and as you can see here, task-wise, that takes roughly 15%, 15.6% of the CPU is done handling this. Now let's see, we can see here we gave it plenty of stack space. We can actually modify that. That's why I like to have this information. Let's go down to the FreeRTOS there, and task, we gave it way too much memory. This one, 256 is not necessary. 128 should do the trick. So let's try to generate that. I mean, this doesn't matter right now. We got plenty of memory, but it might matter if we want to do more. We are only using 17% of, that was actually before the calculation. Let's see what it is now. Should be slightly lower. I don't know if that's, no, it will be exactly the same because this is the internal. Let's just see. So now we still have 53 bytes available in the stack inside the Sine task, and it should not change because what we're doing is the same every single time. So that should be okay. Let me show you why that didn't work. Because if we go in and look at the FreeRTOS will allocate the memory on the stack, and that is actually in one of the config parameters. Where do we have it here? Memory management setting, total heap size. So it will allocate that size no matter what, and then FreeRTOS will allocate space within this one. So what we changed was actually the heap used. When we lowered that, we changed the heap used, so there are more heap space available. That means we could actually lower the memory usage. Actually, let's do that. So let's set that to 10,000 instead, and try to generate the code now. So it used 21 0.88K here. Now let's try to build the project. Should use less now. Does this need to be reversed? Okay, I have no idea why that didn't show up. Oh yes, I do. Of course, I'm stupid because this is not statically allocated. This is allocated on the heap of the STM32, which is the space available between the stack, which is at the top of the memory, and the static allocation, which is at the bottom of the memory. So if we look at, it won't show up in the calculation, but if we look at the memory details here, let's zoom that in, you'll see that we have the data allocation down at the bottom. We're using that much. We have the BSS, which is DMA buffers and stuff like that. And then we have the stack, which is at the top of the memory. So it will not show in the memory usage. It's not constant. So anyway, that is pretty much it. We managed to create two beautiful sine waves using FreeRTOS and callbacks from the core peripheral using an interrupt and get it back. So we show how to synchronize FreeRTOS with the STM32 peripheral using an interrupt and getting it all to play nicely together. As usual, I would really appreciate if you would like and subscribe to this video, to this channel, and like the video. And as usual, I love comments, and I reply to all the comments pretty quickly at the moment. So I mean, please comment below. I do like to get requests for future videos. I won't promise that I'll do it right away, but it helps me form some ideas on where to go next. Have a wonderful rest of the day.